So we're going to start our discussion of these different Java fork join programming paradigms or programming models by demonstrating the applyAllIter example. And as we'll see, this example uses work stealing to disperse tasks to the various worker threads in our custom fork join pool. And you can take a look at that in the EX22 example in my GitHub repository. So what this does at a high level is it's passed in a function, which is the op for the operator, and it will apply the op to all the items in the list parameter by calling fork join methods iteratively. And you can take a look at the implementation in the fork join utils.java file that's part of this repository in my GitHub account. These parameters that are passed in are treated as so-called effectively final by variables in our anonymous inner class below. Effectively final just means that they're not set between the point where they're not reset between the point where they're passed in and where they're actually used. You can see here that we're going to create ourselves a new anonymous recursive task instance. Remember, we talked about recursive task. That's the subclass of fork join task that comes defined out of the box that has a compute method to do some work. And remember that recursive task returns a result. And you can see in this particular case, the compute method returns a list result. Unfortunately, because of the fact that these mechanisms were defined in the earlier days of Java, before we had functional interfaces and so on, we have a little bit more verbosity than you might want normally. And that's because we have to use anonymous inner classes rather than using lambda expressions here. The way we're actually going to kick things off to get it to run in the fork join pool is by using the invoke method, which is that two-way call method that's defined in fork join pool. And what this will do is it'll go ahead and invoke this anonymous inner classes compute method, this tasks compute method, and then it'll block waiting for the results. So this is a blocking two-way call. However, all the computations that are going to take place inside of compute will not be blocking calls. They're going to use the fork join pool to do the processing in parallel. So to illustrate that, let's take a look and kind of zoom in the compute method. This is just the compute method that's defined here inside of that anonymous recursive task. Just kind of splitting it up or zooming in on it so you can see it better. And this is the hook method that implements the main fork join task. And you can see what it does is it makes a new linked list that is going to hold the forked tasks as well as hold the results. And you can see that the forks variable is a list of fork join task objects, and res is a list of result objects, both of which are handled with linked lists. I could have used array list, but I'm using linked list. No big difference. Now what we're going to do, and this is what makes this the iterative variant, we're simply going to use a for each loop to iterate through every element t in the list that's passed as a parameter. And for each of those elements, we're going to make a new anonymous recursive task instance. And we're going to go ahead and define its compute method, which as you can see here is basically defined to apply the operator on each of the elements in the list one at a time. And we're then going to add that new recursive task to the forks list. And then we're going to go ahead and fork this recursive task. I guess I should say more specifically, we're going to create the recursive task, we're going to fork it, and then we're going to add the result, or we're going to add the recursive task to the forks list with the forks variable. When we fork, what that does, if you recall what fork does, that arranges to execute this recursive task in the common fork join pool. I'm sorry, in the fork join pool that's part of this particular context, which is the context of the outermost fork join task. So you can see here, that's what we have there. We have the new recursive task. That's the context in which this is going to run. And that's being invoked in the context of the fork join pool that is passed as a parameter. And the invoke method is a method that's going to take a non-fork join task client, which is this outermost thing, and then get that to run And then henceforward, everything that gets run inside of this will now be running in the context of a worker thread in the fork join pool that was passed in as a parameter to the applyAllIter method. It's a little confusing at first, but if you think about it, it makes good sense. This particular implementation heavily depends on work stealing in order to disperse the tasks to the worker threads. And that's because every one of these tasks that we're forking here originally starts out in a single worker thread's deck. So we're going to load them all up in a single worker thread, and then all the other worker threads are going to come and steal from that single worker thread's deck. Now, at this point, everybody's off to the races running in parallel in different worker threads in the fork join pool based on stealing. We'll look at that in more detail in a second. So what's left for the outermost compute method to do is then to do a form of barrier synchronization where it's going to join all the results of the fork tasks and add them to the results list. So you can see here it's going to go through the forks variable, the forks list, and for each fork join task in forks, we're going to say result.add task.join. And if you recall, remember task.join logically blocks, doesn't physically block. That calling thread pitches in and does processing until we get the result for that particular task. And then that result is added to the results list. And after all of this finishes, because again, it's a barrier, then we return the results list as the result from the applyAllIter method. So all that computation that we see kind of in the middle will all run in parallel, and then we'll join all the results and return the finished list that contains all the results. This implementation is very simple to program once you understand the idioms it's doing. And it's relatively easy to understand because it's iterative. We're just walking through, forking as we go. Those things are going to run in parallel in an embarrassingly parallel manner. And then we have this second loop that just waits for all the results by using join and adds them to the list of results. So let's kind of visualize this a little bit. Sometimes it's easier to understand things if you see what they're doing as opposed to just reading the code. So this is what we're going to do. We're going to have the left-hand side will kind of be snippets of the code that we just looked at, and the right-hand side will be a visualization of what's actually taking place under the hood for this particular fork join pool that we've got. So the first thing that happens is we call fj pool invoke, creating a new recursive task. Remember, this is from the non-fork join task client's perspective. It inserts this anonymous recursive task into the fork join pool's shared queue. So now it's in the queue. And then we go into the compute method. And what happens, of course, is that one thread, whoever the thread is that handles this compute method for this outermost recursive task, that particular thread will then run the code I show here in red, which is the for each loop, and it'll basically throw all of these other recursive tasks, which are the inner ones, into its work queue or its deck. So let's say this is worker thread 1. It's going to go ahead and put all those other pieces into its deck. And that's all going to run inside the worker thread 1's context. Well, at that point, once it does all this, then it'll go into that second loop. But before that point, or even as that's running, the threads that are also in the pool are going to look around and go, gosh, there's a thread here that has an awful lot of stuff in it, and it's not going to be able to process it all by itself. Let's start stealing. And so those other worker threads are going to start stealing the tasks from the end of worker thread 1's deck. So remember, they get stolen in so-called FIFO order. So the nice thing about this is that there's very little copying, there's very little method call overhead, but there's a fair amount of work stealing because we have to rely on work stealing to propagate the tasks from worker thread 1 to all the other worker threads that are in the pool. And that takes a little while. And as you'll see, it has some detrimental effects on performance. Then when we go into the main loop here, or the second loop, where worker thread 1 does the barrier synchronization, it's going to call join repeatedly, and it'll pitch in. So worker thread 1 will pitch in to do some computations when join is called. only returning from join whenever that particular task's results are known. So this is what I like to refer to as the Jiffy Lube model of the collaborative Jiffy Lube model of processing results in the fork join pool. You can basically think about this second loop as a barrier synchronizer, as we've mentioned before. So that's the end of an overview of the applyAllIter method. This one, very simple to program, relatively easy to understand, but it has a lot of work stealing, and therefore, as we'll see when we look at the results later, doesn't perform as well as we might want, especially relative to other ways of doing things.